Hi, this is Stuart, and today we have another video, Modern Development, some notes from the field. So I've been a developer for almost 50 years. I started when I was a small child building things, and I have been working as a professional developer for over 30 years. And what I've noticed is things change. So I wanted to come back and make a video about what I think works today. It may not be the best thing that works tomorrow, but these are some things that I think are the table stakes for modern development today. So we have this idea that as systems get bigger and bigger and more interconnected and complicated, that you need enterprise architecture, but you also need DevSecOps. And that stands for Development, Security, and Operations Best Practices. And we're going to drill into what that is in the video. But if you don't have that, the chances of you successfully delivering a large-scale enterprise project are a lot lower than if you kind of bit down and did some of these things. So I wanted to revisit software development foundational ideas. And some of these are fairly new, and some of these are as old as time. They go all the way back to the first emergence of object-oriented design. And so let's just go through the list. And we'll talk about each of these topics in little bite-sized chunks. And then, so the 12-factor net is essentially a manifesto, in the same way that the Agile Manifesto called out some high-level principles about, in this case, how to design and implement systems that are going to be very durable and very well made. So you can read on 12factor.net and drill into each of these, and we're going to be hitting some of these as we go along, but I wanted to visit three of them that are often not paid much attention, and that is, I wanted to talk about backing services, this idea that everything that your application needs is a service. So databases, queues, file storage, and of course service, traditional way we think about services. If you think about everything as a service, the chances you'll have a decent enterprise architecture is excellent. And process statelessness is the key to enterprise architecture. It's not saying that you can't build an application with state. It's that in between interactions, the state should dehydrate and rehydrate or be fetchable from somewhere and so on. And that goes along with disposability, the idea that our processes can be ephemeral, they can come and go, we can add more process instances as we need to scale, and we can drop them, then they're not scale. And so we have to design things with disposability, things that don't hold on to data in between operations, at least at the application level. We're going to talk about other things as we go along, other than to say that if you have one system that runs jobs and tasks and another system where you run your applications, you've missed an opportunity to consolidate your architecture, but also to make reusable components that developers can then leverage to very quickly add new capabilities, especially in the scheduled task and headless process area. So Solid is very old. You can go read up on Solid. But everything about the Solid principles is still true in modern enterprise architecture. Single responsibility and microservices, right? Those two things they're conceptually quite close. The open-close principle that we can make things by extension, whether that's by composition or by actual extension. The fact that we want to have contract first development, that's the Liskov substitution principle in action. Interface segregation principle, right? That we have fitness for purpose, that something does one thing and does it really well, and that we use interfaces to describe data and behavior, and of course, dependency inversion. So we have this lemma, right, called keep it simple and steady. And complexity is the enemy of good software systems, strong coupling, and so on. And one of the things that hasn't changed about a subset of developers is their affliction for coolness, or adding things they're not going to need. There's this thing called the agony, which is you aren't going to need it. And that is only adding levels of indirection or software features when you identify that you have an actual use case that would be hard to support without them. That these things should come out of refactoring, and that we should start as simply as we can, and that less is always more, right? If defects are roughly a function of lines of code, and I know that's kind of an old way of thinking about code, but it's still true that the more code you have, the more defects you're going to have, right? So less is definitely more. And then one of the most important and pivotal areas that's deeply influenced the design thinking of enterprise architects is Eric Evans's beautifully written tome on domain-driven design. There's a domain-driven design handbook that's very small and easy to carry around with you on your e-reader, that is good to refer to while you're thinking through architecture and design problems. And the output of domain-driven design spawned a lot of things like RESTful architecture and microservices and decoupling via queue mediation and so on, right? That if we understand where the domains are, what the domains are and where the boundaries are, that we're going to have much better software. So this is an old book, but it's still worth reading, and I try to reread it once a year. So microservices is the output of all these things, right? Microservices hit solid, they hit domain-driven design, they hit simplicity, and the idea is that a particular service interface does one job, does it really clearly and very well, and that you, in a perfect universe, they're self-documenting, and that you shouldn't need a brick-thick book to understand how they work. And so, which is not to say that they can't be built on the same set of interchangeable, reusable libraries and so on. And one of the things that is probably the hardest design decision in the enterprise space is aggregating microservices on the same host so that we can have the most efficient use of resources, versus having each microservice hosted itself and having them truly be able to scale independently of each other. And that's always going to be a trade-off. So even in writing the code hosts for a microservice, if you think about .NET, it has this idea of a controller. And so if we consider each controller to be a microservice, right, that the methods inside the controller, inside this class, are going to be the operations that can be performed against the entities that we're representing in our microservice. It's because of the amount of plumbing and the overhead of the runtime and so on, it may not be efficient to host one controller per deployable unit. You may want to aggregate these things together, particularly if one microservice calls another, if we have an aggregation pattern or a facade pattern. So the lumping and splitting problem, which is the classic thing in computer science, comes into the actual implementation of microservices, but at the design level, we think of them as being independently coupled from each other. I'd also point out that if you're implementing a microservice pattern over an existing set of schemas, which is a great way of getting started with microservices and also making it clear in the minds of the stakeholders what the different domains are, that you may not have the luxury of splitting up that monolithic database, but you may have the luxury of starting to gently tease it apart with namespaces and so on, that at least at the logical level, even at the physical level, if they're co-joined, that you can start to have some logical separation. And that also makes things like views and stored procedures and queries easier to read, because once we add a namespace in front of the object and that namespace corresponds to our domain, then it's a lot more obvious when we have interactions between domains. And we can look at a statement and say that a statement affects a single domain or a statement is cross-domain in nature. And that gets back to the ideas of reusability. Reusability used to be really a hard nut to crack, right? When the concept of reusability first came out, there just wasn't a lot of tooling support for reusability. And a lot of reusability is still in use today, and that's copy-paste, right? We find a little snippet of code on the internet, we copy-paste it, and we have reusability. But we also have new ways of, the whole restive microservices pattern has led to services as a mechanism for usability, that we can have shared services across business units like address verification and geolocation and payment gateways and domain-specific services that provide data and actions for us. The fact that almost every programming language on the planet except for Java has a package manager, and that there are public package repositories that you can share your reusable code to if you want them to be open source, and that it's now very easy to bring up a private repository inside your private space, make it a ton easier to have reusable code. And most organizations have both. They have community contributions that are on the public NuGets and NPMs and gem sites, and then they have their own internal repositories that have their intellectual property that has domain-specific things for their organization and so on. Datagram standards are another reusable thing. If we look at even the lowest level protocols that enabled the internet, those constitute a datagram, right? We have a datagram for what an IP packet looks like. We have a datagram for how TCP assembles those IP packets into a coherent message. We have a datagram that constitutes the standard for HTTP. What does the HTTP protocol look like? We have a datagram standard for HTTPS and so on. And so a combination of actions and datagrams make a protocol, and protocols woven together make patterns of a kind. And so reusability is best when we share it. So when we're thinking about architecture and design, we came up with this thought, and the thought was that if you go out onto the interweb and you look for lists of abilities, that you'll get lots and lots of different variations. But what we came up with was, hey, what is the minimum number of abilities that we could talk about and have virtually 100% coverage of all the abilities that we care about? And it turns out that if you're willing to accept the idea that two of these super abilities combine to make a new ability, then you can boil down your list to 10 abilities. And that's what we did. And you can argue these all you want, right? You can make your own lists with whatever you want on them. But this is ours that we've come up with. And so, during the inception process for a project, we talk about these 10 abilities, and instead of having to talk about 50 abilities, we can talk about 10. And so we can socialize what goes in each one. We can combine them to make new abilities that express a business need or a technology need. But, these 10, as far as we know, cover pretty much everything there is to know. And by thinking about the abilities of a system first and foremost, and to some degree stack ranking how important each of these abilities are, goes a long way to making sure that these core non-functional requirements are thought of before we even write a single line of code. So abilities first is the natural starting place for an architecture and design to solve a business problem. So there's this lemma. And the lemma says that you can't sprinkle quality and security onto the software as an afterthought. And that goes for all the non-functional requirements, testability, operability, and so on. You cannot add them as an afterthought without traumatic levels of refactoring. And there's a famous graph, right, that shows that the further on in the development process you do something, the more expensive it gets. And depending on whose graph you're looking at, that can be either exponentially more expensive or geometrically more expensive or some other curve. But the later you put these things off, the more expensive they are when you need them. So it's important to think about abilities early and always, and constantly be revalidating the non-functionals as well. And that's an important role that Dev, QA, and Ops share together. There's been a lot of development practices over the years, and I've been through all of them, from early waterfall to the horror of RUP to lean, agile, Scrum, all of those different ones. And I can tell you that the success place they all have in common is short, sharp stanzas, right? You want to be lean, be Kanban, be Kanban. I'm going to show you Kanban in this example because I don't think enough people spend enough time talking about it's technically Kanban. But I want to point out that you want stories for developers to implement that are in the extra small and medium t-shirt size domain. And if something takes longer than 2 or 3 days for a developer to knock out, the story is too big. And one of the hallmarks of bad development is coders starting to code on things that are not well understood. One of the hallmarks of bad development practices is developers starting to code on things that are not well understood by both Dev and QA, right? We have to have a shared, in order for QA to test something, Dev and QA have to share an idea about the story that expresses the same thought. Otherwise, QA is going to be testing one thing and Dev's going to be testing another, and you're going to have a lot of defects. Defect doesn't mean you coded something wrong. It just means that QA doesn't agree with you. So we want to avoid that. We want everything to be short-lived, right? And we're going to talk about feature branches when we get to it. So I wanted to take a look at what are the essential items in a story card. And you can have as many variations on this as you want. You don't have to do it this way, right? But there are some essential things that you want. And probably the most important 2 things are a unique ID of some kind, so that we can, as a shorthand, say, oh, I want to talk about blah, 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 blah. And everybody can go look it up and see what it is. Titles change, values change, descriptions change, comments change, criteria changes. But if we have a unique ID, at least we're talking apples to apples. And acceptance criteria. This is an area that is where most of the pain happens. The better your acceptance criteria, the more likely it is that when a story gets developed, that they'll be developing the right thing in the right way, and that QA and the business will both agree that they did. And I'll also point out that stories should have business value. If there's no business value for a story, then we have to ask, why are we doing it? And sometimes the business value is compliance says we have to. Okay, well, they can't ship without their blessing, and therefore there's business value to be had there. It's important that there's this gate that says that a story is ready to be developed. And this, I think, is an area where, especially in sprint-based development, that in the haste to get ready for the sprint while you're trying to finish the last one, which is, I think, adds a lot of ceremony that doesn't need to be there, that we don't focus on whether or not a story is dev ready or not. So here's why you'd want to reject a story. It's incomplete, right? The developer looks at it and goes, I can't figure out what I'm supposed to be building. And missing acceptance criteria is the big red flag there, or acceptance criteria that is untestable, right? It's too big. It can't be done in 1 to 3 days. 1 to 2 days is ideal. 3 days is stretching it. You can't, if it can't be coded at all, if we look at it and we go, yeah, that's great, but it violates this non-functional, right? Or we're waiting on something, right? There's a story that's a prerequisite. It may have lower business value, but it's a prerequisite to this story. Or it's blocked by something, right? So we shouldn't be afraid of rejecting stories as developers, right? We should go, look, this is a perfectly okay story, but it needs this, 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 and this, right? We're not going to do it. So if we think about, and again, you can have whatever Kanban lanes you want. This is the one that I favor, and I try to use when I can convince my customer to do it this way. But we have this backlog, and the backlog should never be empty, and it should always be the place where any stakeholder can put a story anytime. There shouldn't be any gating on the backlog, right? We want to capture ideas. We don't want to lose them. So by all means, make a story card, put it in the backlog. Now, no one says that that story is going to actually get developed or shipped to production, but we haven't lost the idea. So then there's this thing where we go through the stories and the business looks at the backlog and goes, based on our assessment of the business value of this story, we think these are ready for dev. And so at some cadence, you get together in a room with dev, QA, and the business, and the business presents the backlog stories that they think are ready for dev. And again, we don't care if the ready for dev column has 20,000 things in it, as long as they're sorted by business value, so that we, as developers, when we grab stories, we grab the thing with the highest business value. Right? And if that story is blocked because there's a prerequisite, we go through the ready for dev list until we find one that is codable, right? We go from the most business value to the least business value until we find something we can code. So the backlog should be enormous, ready for dev should be enormous, and the gate for ready to dev is that dev and QA agree that the story exists in sufficient detail that it could be coded and tested. And then, dev grabs stories as they finish the story, they grab the next story. When they're done, we put them in the ready for QA pile. And in between the coding and ready for QA is a process, and we're going to show you that in a minute. And then QA says we're testing it. And then we say, okay, we've tested it, and we bless it. If they don't bless it, guess what? It gets a new story generated called a bug, and we staple it to the original story, and we throw it back in the ready for dev pile. And then we throw it into the ready for UA, and at the same time, when things are ready for UA, they're deployed to a preview environment where the business can look at it. And when the business moves those stories into the releasable pod, then those things are going to go into a staging or pre-production pool. And then when the business is ready, they can flip the switch, and what was staging becomes production, and what was production becomes the previous staging, and we ensorcel that away until we're happy that what we've sent to production is stable, and then we start releasing things into the staging slot or area again. So this is the basic Kanban board. It covers the fundamental processes, and you can see what the gates or processes are at the bottom of each one, which brings me to branching. many organizations that are dysfunctional have way too ornate a branching strategy. And the way you can tell your branching strategy is too ornate is it's more complicated than this. And or you have the moral equivalence of feature branches that are very long-lived. And remember, our goal is a day, even sub a day. You know, really good organizations split stories into such small, snacky sizes that feature branches last less than a day. The goal is, of course, that we have this gate between the feature branches and the main develop pipeline, and between the develop pipeline and the master pipeline, and it's no more complicated than this. So if you go look at your existing branching structure and it's super complicated, you have to ask yourself, what is broken about your process that has the branches live for so long? And what assumptions, probably false assumptions, are you making about your source control system that makes it impossible for you to recreate what was sent to an environment without having a branch? So, and we're going to talk about that. But at a minimum, systems that don't support labeling are god-awful. My favorite source control system is Git. Should be your favorite too. It is the future of source control. Embrace it now, and just, if you can, get off whatever horrible thing you're using. And I'll point out that all the big boy software development shops on the planet Earth, including Microsoft, now use Git. So a typical development process, right, working with a source control system, so we're going to assume Git here, is they're going to go to the develop branch and they're going to do a Git pull to make sure that they have the latest possible source that is stable. The origin development branch should always compile, should always pass all the tests, should always be stable. And they're going to pull a copy of that down to their local machine, and they're going to create a topic branch to work in, switch to the topic branch, and then push that topic branch up to the origin again. This is hub and spoke development, which is the reality for most commercial shops. So this is not intended as a model for the open source community or whatever, but if you're working in a commercial shop for a company, you want to make sure that that intellectual property, that work stream value that you spent money to make is somewhere safe, and typically that's the origin. And then there's this little loop that says do a little work, test your work, commit your work. And you can do it, write a test, write the code, write a test, write a code, or write some code, write a test, write some code, write a test. But when you commit, right, when you take a collection of changed files and you make a commit out of it, two things should be true. One is the code should run, and two is that there should be tests and code. And then you should commit it and push it to the origin. And where you're pushing it is your topic branch in the origin, right? And you want to keep doing that. And why are we pushing the code to the origin at the end of that little loop? So that if something horrible happens to your machine, or you're hit by a bus when you leave for lunch, that the rest of the team can recover your work and merrily go upon their way. And in a well-tuned team, people are doing this little C cycle 3, 4, 5, 6, 10 times a day. I've done it. If I'm on a hot coding streak and I'm coding for 10 to 12 hours at a time, piles of Diet Well Cherry Pepsi cans piling up by my desk, I will have 10 to 20 commits in a day. Code a little, test it, when it works, commit it and push it, repeat, repeat, repeat. And the tooling makes it incredibly easy to do, right? If you're a .NET developer, as many of the people who follow my channel are, you've got Visual Studio, you've got the free Visual Studio Code. If you're a Java developer, all of the great Java IDEs have similar things. They have really good integration with Git, and there's no excuse for not doing this. When you're done, when the story is done and the tests all pass, then you do a pull request. And people peer review your pull request. And then your pull request goes through a checked build. And if the build passes, it goes into the develop branch on origin. And the process repeats. And you can delete your topic branch or reuse your topic branch or whatever you want to do. So I tend to delete mine and start over. And so my topic branches tend to have my name and then a hyphen and then my story card number, so that I know what story a topic branch is for, and I can have as many topic branches. If I'm interrupted to do a hotfix or something, I can park my topic branch and either stash it if it's not ready to push to origin, or push it to origin if it is, and switch branches and make a hotfix branch and do whatever I have to do, and then I can resume my work again. So I have a pet peeve about testing, unit testing particularly, and that is people don't ask the fundamental question: if this test fails, what does it mean? What does it tell us, right? What is wrong with the system if this test fails? If there's no risk consequence to the test failing, it's a useless test. It just takes up space. And the chances that, as we add more and more tests, we're writing more and more code, right? Tests are code. The more code we have, the more defects we have. So by writing a bunch of useless tests, we're just increasing the chances we're going to have a defect. So do risk-based testing. Test the scary stuff. Test the must compute correctly stuff. Don't test stupid stuff. DTSS. So in .NET, if you have public string last name get set, don't write a test for that, because it's dumb. It will always work. The compiler will make it so, and if it doesn't work, something is so heinously wrong with your runtime environment, nothing else will work either, right? You don't test for the impossible. If you write a unit test for being out of memory in your runtime, you're mentally ill, right? Don't test the things that you have control over as a developer, right? And that brings me to mocking. I have seen, mock's great, don't get me wrong. I think mocking is a very powerful thing, especially for writing a unit test that's actually written as an integration test. So we write something that's fundamentally an integration test, except that our services, remember that, everything is a service, is actually a mock, so that we can focus on testing the thing that we need to test, some business logic or whatever. But I've seen things that are so heavily mocked that they don't actually exercise any business functionality, and when they pass, they don't tell us anything, and if they fail, they don't tell us anything other than we mocked incorrectly, right? We have made a mockery of our test. We have overly mocked stuff. And then people get, especially organizations, they're so keen on metrics. I love Deming, right? I love the Toyota system. I love it, I love it, I love it. And there's this rubric that you cannot manage what you do not measure. But there are things called false metrics. And coverage can be a false metric if teams obsess about it. So if your code coverage is less than 50 to 70%, you may or may not be testing the risky stuff. And you should look at that, right? Ask what parts of the risky stuff aren't we testing? But above that, you may be testing artifices of your coding framework. You know, trying to test the catch block is a common pattern to try to get those code coverage metrics up, and it's dumb. First of all, most code shouldn't have a try catch in it, right? We should let some top-level error handler manage exceptions. Exceptions should truly be exceptional. And second, never ever catch something you're not prepared to handle. So if the only reason you're catching something is to log it, then that should have been done at the top level log handler, right? The thing that, the process level. We want to fail fast to that level. So if the only reason you're catching something is to log it or to rethrow it, both of which are dumb, you shouldn't have had a try catch block in the first place. You just shouldn't. You should have just let it fail. Fail fast. So what that does is, the side effect is you can write a lot fewer tests and you'll actually end up with better code coverage, because you can write a test that tests the global exception handler, which handles the exception based on exception type and does the appropriate logging and in whatever, right? So DevSecOps is table stakes. Deploy frequently. There's no excuse for not doing that anymore. It used to be that it was super hard, but now that we have Kubernetes and PCF and Docker, and we have environments in Azure and GCP and AWS and all of our other favorite hosting, and we can have as many environments as we want, and we can have them whenever we want, and we're going to talk about that, then there's no excuse for not doing continuous deployment. And in fact, I will stipulate that you cannot test what is not deployed. So you can do unit testing, but past unit testing, you're probably not going to get useful testing stuff unless it's deployed into the real world. And what you're doing is integration testing or end-to-end testing. Logging, you're doing it wrong. All those logging frameworks you made, if you have a decent runtime environment, Java, .NET, PHP, whatever, they have a built-in logging mechanism that knows how to log bad things to standard error and good things to standard out. For the love of God, use them. And if you're running on Azure, GCP, Docker, PCF, blah, 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 those environment hosts are capturing that output anyway. So just do that and roll it up. Use your favorite log aggregator, either the one provided by your platform, or if you need more capability, a Splunk or whatever. So monitoring is a must, right? If we're deploying to over there somewhere, we have to know if the thing's alive and healthy. And so exposing a health check is super easy. And most programming languages and frameworks have a way of exposing health checks. .NET Core just added a bunch of very cool health check stuff that allows you to expose health check endpoints even for headless processi, which is extremely cool. And most other frameworks have something that you can use so that from the outside we can do a probe and say, is this process healthy? And then you need to be able to coordinate your logs and events from your infrastructure to the application so you can see what happened when something goes wrong in the application, what was going on in the infrastructure. And if you don't test your survivability, you don't have any. So really sophisticated shops can pull a plug on something and everything should keep running. And in fact, Netflix famously has Chaos Monkey. And that sort of survivability testing is super important. And we'll talk about DR and HA in a little bit. This is probably the single most important thing if you take nothing else away from this. Build it once, deploy it many times. An anti-pattern is if you have a build per environment. If that's you, and you're actually recompiling or rebundling or repackaging the code, then you've got to fail. So in a perfect universe, we go through our top line process, which is the developer experience, which includes a pull request, peer reviews, and a checked build. And at that point, if the checked build succeeds, two things are true. One is your feature branch has been integrated into the main branch of some variety. It's usually developed. And secondly, those build artifacts are captured and stored in an artifact store. And then whenever we want, we can do the bottom line process. We can pick an environment, pick a set of build artifacts from the artifactory, deploy them, test them, and use them. And sometimes, depending on the environment, testing is the point. And sometimes, depending on the environment, using is the point. But either way, we are not recompiling a fresh set of code. And this pattern opens up a world of goodness. World of goodness number one is we know that the code for release candidate 459 that was stored in our artifactory in the 459 folder is the same code that got deployed to dev integration, and the devs played with and said, verily it is good, that the QA pulled into there from the artifactory again. They pulled that same build, 459, in the QA environment, and they said, yea, verily it was good. And then the business said, oh, QA says 459 is good, I shall pull it into user acceptance testing by clicking the pull it into my environment button. And I say, yea, verily that is good. I wish to have this flow into staging. And so they click the button that says, I will flow this into staging. And then when they decide, they flip the switch that swaps staging and production, and they have done a production rollout. And none of us need to be involved. Isn't that wonderful? So, this assumes your app's a 12-factor app, though, and that your configuration goes with the environment and not with the code. Pull requests. So we talked about this before, right? We do a pull request, we do peer review, and if your story size is really teeny, then this isn't arduous, right? This takes 10 minutes at most, because there's not that much change to deal with at once. So on projects that do this, I set aside 3 periods a day to do pull requests. Usually first thing in the morning or right after Scrum, I'll do a wave of pull requests. I'll do a wave of pull requests before lunch. I'll do a wave of pull requests after my afternoon break, and I'll do a wave of pull requests right before I go home, along with updating my story, my time card, thinking about what we need to do tomorrow as a team, that sort of thing, and getting ready for our group hug the next morning. So because the amount of code that we're reviewing is small, they shouldn't take very long, and the risk of integrating these via checked build that you saw on the last slide is very small. By the way, done equals the code is done, it's got tests that pass, and we've done whatever our shop standard says we need to do for static code analysis or whatever, right? If we're required to run Veracode, if we're required to run FXCop, if we're required to run StyleCop, this is done. That's what, you're not done till those things are done. And there's no such thing as done. You're either done or you're not done. It's a binary condition. And done means that your code has joined the develop branch. That's what done means. And if your code is associated with a defect, there is a new story. Yeah, you heard me. So, what's in a good build? I call it the W. Pull the source, do the build. For some programming languages, this is less a build than it is some sort of assembly or packaging process, but that's okay. For Node.js, for example, a build is way different than a build for .NET. Is different than a build for Java, right? But we're making sure that it's packageable at the end of the day. And so that's part of the build. And we do a static code analysis. God willing, we do a security scan. We do tests. And by the way, we want to fail early if we're going to fail, right? Because the downward side of the W, the rightmost V, happens basically after all the tests pass. That's why it's in this pattern. We want you to think about the left V and the right V. The left V are places where your build could fail. The right V should never fail, unless your infrastructure is just boink for some reason. So then we want to version. We want to use semantic versioning. So our build should be incrementing our patch. And if you're using .NET, the build number. and patch should be incremented at intervals, but we should use semantic versioning. And then we need to package whatever we need to do to package that. It may just be that all of the output got built to a particular folder and we need to roll that folder into our Artifactory, whether it's a nest of file folders or something schmancy. And then we need to have a build report that says what happened. That's what a good build looks like. It's called the W. And again, the left V is where failure happens. The right V should never fail. So if we're going to deploy one unit, what does that look like in the new universe? Well, what it looks like is we spin up an instance of a host, and we go into our configuration store in our secrets repository, and typically we inject those as environment variables into our host. Remember, in our 12-factor universe, that configuration goes with the environment, and a host is a running place to run code in an environment, right? And then we go into our Artifactory store and we pull the deployable unit out of build 459 and we inject it and turn it into a running application, and our running application starts and reuses its information. An alternate but perfectly valid pattern is we don't inject secrets and configuration in environment variables, and instead the running application is deployed from the Artifactory store, and then using service discovery it finds the configuration and secret services and asks for its configuration during startup, gets the configuration and secrets it needs, and motors on. Those are both equally good patterns. The first one is a little bit more debuggable in my opinion, and but both are supported by virtually any modern hosting system. So let's talk environments. You should have some. So on the right side, we have different people in different roles, and those same people in same roles are on the left side as well. And then down the center, we have the environments. Here's the minimum environments I suggest. You can have as many more or fewer as you want. This is a conceptual thing. So in the dev environment, developers should have free reign. They should be able to deploy on demand. They should be able to inspect any of the data, events, logs, whatever that come out of that. They need to be able to do that like crazy monkeys over and over again. In many cases, in sophisticated shops, developers have their own sandbox, which would be above dev. And in fact, dev is not in fact built by the developers. It's built by the build deploy robot instead. But developers need a place where they can free play. They can do experiments. They can try stuff that fails. And they can learn from that failure and write better software. And then on the right, we have this who can trigger a deployment. This idea that we can press a button, and before we press a button, we pick a release candidate from our list from our Artifactory, right, where our build artifacts are stored. And so QA can go and say, hey, I see that release candidate 459 is available. So they pick 459 in their little dashboard and they hit deploy that to my QA environment. And if they have multiple QA environments, which is pretty cool, then they would pull the pull down and pull which QA environment they want to deploy it into, and they'd hit the button, and that would tell our friend, the build deploy robot, to build out the QA environment. And if you're a really sophisticated shop, the build deploy robot will tear down the old instance's infrastructure in its entirety, repave it clean, shiny, and new, and then do the deployments. And the business can say, hey, 459's been signed off by QA. I want to deploy that into UAT or stage or production. And they make the request and they can do it. And so can our friends in DevSecOps. And sometimes DevSecOps has their own morally equivalent environment between UAT and stage they can interoperate with. But notice in the upper environments, although we can request a build, the only people that can do a build is the robot. And on the left-hand side, the robot in all of the advanced environments does the aggregation and then exposes a way of sharing the data. So we have a dashboard, a single pane of glass that stakeholders of any variety can go through and look at the data that's coming out of the environments from our running applications and the infrastructure. And this is what Nerdvana looks like. So infrastructure is code, right? We started to talk about this already, and there's no reason not to do this anymore, right? The tooling is there, the documentation is there, communities are there, support is there, and in really well-running universes, organizations are capable of either repaving on demand. So that example where QA says, I like build 459, and the robot says, Roger, Dodger. And not only does it do a clean deployment, but it starts by flattening, deleting, scrubbing the existing QA environment, or potentially building a new one from scratch if you want to do a rolling environment type of pattern. And it deploys all the infrastructure. And that includes deploying platform as a service instances and hosts and databases and queues and storage and whatever it wants. But we repave. And then our code 459 goes on top of a bright, shiny, freshly scrubbed set of infrastructure so that we don't have the problem where we're deploying on top of something we've already deployed upon and something icky happens because of the result, right? We want to start clean, and so having infrastructure as code and repaving as we go on our environments will never give us woe. You can even repave production if all of the components in production are scaled out, including your database. So I can pick a victim host. For example, I can pick an app server, and I can say, I kill thee. And what happens is, in the script, we say, dear load balancer, please don't assign any more work to this. Or, dear process, please, if it's headless, dear process, please shut down and don't process any more requests. And then it waits for that to be true. And then it nukes the thing, right? And builds another one. And sometimes, depending on our environment, it may build another one first and then pick one to victimize. That's even more better. And we can do this in production. So for example, if you're a Postgres shop and you're running CockroachDB, and our CockroachDB instance is a cluster of clusters scattered over 3 data centers. They're geographically separated by 321 miles. And at each data center, we have 5 redundant instances. We can just randomly kill one, and it will keep running. And then we can repave, right? We can add a new instance to replace the one that died. So that's a failure type scenario or HA scenario. Or we can bring up one proactively that maybe's got some new patches, and we can join it to the cluster and we can watch it for a while. And if it looks like it's cool, then we can mark that one as okay and repeat. And we can continuously repave everything in our environment from front to back over and over and over again. And this is how we do patch management, and this is how we make sure that everything is clean, and this is how we make sure that the previous deployment doesn't leave garbage behind for our next deployment. Clean is as clean does. Work clean is what they teach you in the kitchen. And of course, if you have, and you will, secrets that go along with that, connection strings, things that applications might need, certificates and keys and API keys and whatever, but infrastructure has secrets too. And so having a secrets repository that the repaving robot can use to pull from to make sure that our things are set up correctly is great. And repaving is also a way that we can do cryptographic rotation and things like that. And everything keeps running. You have a perfect enterprise system can suffer a traumatic loss of a data center without anyone noticing. Now, you may have some initial performance things or whatever, but if you're really good, no one should ever notice. And the proof of that pudding is in the eating, in the repaving, right? If you can continuously repave, you can survive a traumatic incident. So one of the things we like to say is death to DR, right? If you have to do disaster recovery, then you haven't built an infrastructure that spans data centers that is survivable, right? So DR as a concept is now expressed as multiple redundancy with 2 out of 3 survivability, right? That is, and 5 years ago, this was really hard to do. 3 years ago, it was hard to do. 2 years ago, it was getting better to do. And now there's just no reason not to do it because almost everything is built for that tell me twice out of 3 times survivability, which is why, by the way, everything should have an odd number of instances. If you have manual steps in your provisioning or your deployments, your organizational maturity is not what it could be. Harsh but true. Unified monitoring. I've seen a lot of customers, and they log like banshees. And then I look at their logs, and I conclude 3 things. One is, InfoSec should come looking for them with an axe because they're logging stuff that breaks HIPAA or PCI or logs the actual connection string with the secret in it. No. The second thing I notice is the logs are worthless. I look at the log and there's a log entry and I don't know what that log entry tells me. So a bad log entry would be an order was processed. A good log entry is order 574 was processed to provisioning for customer code X57B. That's a good log entry, right? Logging the actual exception in stack trace. That's a good log entry. But most of them are useless. And the third thing I notice is there are no logs. There's no logging. There's no logging anywhere. Or they're misusing the logging standard, right? There's a standard pattern for logging now, right? Critical means that the deployable unit cannot function correctly until intervention happens. By the way, it doesn't have to be physical intervention by a human, just intervention. I am so broken I cannot run. That's what critical means. Error means something horrible happened, but I'm going to motor on as an application, right? So if your application quits, it should be a critical. If your application attempts to reset to some zero base state and motor on, it's an error. And if it's a corrected error, right, you have a try catch because you actually have a problem you can fix, it's a warning. If it is a log entry about business value, it's information. If it's a log entry of interest to a developer trying to figure out what went wrong, it's a debug. And if it's a vociferous, lengthy, incredibly granular activity trace, right? It's a verbose or whatever the equivalent is. But there should be 6 logging levels. And you should use them. The top 3 go to standard error. Sometimes only the top 2, depends on your shop. And the good ones should go to standard out. And so you should have a log aggregator, right? And if you're running Kubernetes or PCF, or you're if you're using PaaS hosting in GCP, Azure, or AWS, they have a log aggregator. So the aggregated logs flow along, and if you have a log aggregation analysis tool, and it's looking at the logs, it's trying to decide if something horrible happened, and it turns that into an event, along with the events and state that are coming from the infrastructure and the environment, like from the PCF or Kubernetes engine, or from the hosting engine on GCP or whatever. And all those things are going into a monitoring place. Typically, those also provide single panes of glass. And in there, we're looking at the data that's coming in, and we're making decisions about whether or not something truly horrible has happened, and should we have an incident to go with it, or should we not? And if there is an incident, we should create a ticket in our ticketing system. And by the way, some of these tickets and incidents can be serviced by robots, right? We go, oh, this particular incident type, the way to fix this is to repave, right? So I'm going to start repaving this broken thing. And in some cases, the repaving happens all the way down in the application environment. If I'm running PCF and one of my deployment app instances goes bad, it will spin up another one for me, and through an event let me know it happened. And that's not an incident. It's just something that happened. An incident would be if it starts happening a lot. Then we probably want to make a ticket and do a notification. And at the end of the day, notifications are for the benefit of humans, right? So if you escalate something all the way to a notification, you've just told a human about it. But our goal is to drive notifications to 0 by making all of our systems self-healing, so that we capture, for the sake of interest, potentially what happened, and maybe it was important enough to be an incident, but we didn't have to do a notification because the robot was a subscriber to the ticket and it was able to successfully resolve the issue, and our app keeps running. If you have your app in any modern hosting environment, there's an enormous sets of streams of data available to you. Logs, events, state. But unless you're consuming it in a coordinated fashion, and then you have something, humans, better yet, robots, watching it and deciding if something is an incident or not, and then causing action to happen. If something bad happens and there's no action, then something bad either didn't happen or you're missing an action, right? So ideally, you have the final finishing touch of modernity is unified, coordinated monitoring with well-defined incidents, which cause a ticket, which cause an action. One of the actions is a notification if it absolutely positively has to go to a human.